Hello everyone, this is Abilino Dawis, your instructor. Let us now advance our discussion on rotor angle stability. Now this time we will consider the relationship of the power uh, generated by our generator with respect to its rotor angle. No? So we will see how the power is related to the rotor angle. So we have here the power versus the angle relationship. Now, first, let us consider the system as shown, where we have a single generator and it's supplying power to a load through a transmission line between bus 1 and bus 2, where the reactance of the transmission line is designated as XL and the current supplied by the generator, which is the current also of the load, as I. So XL here is the reactance of the line with resistance of the line neglected. Now for the power to flow along the line, there must be voltage angle difference between bus 1 and bus 2. So uh, at bus 1 we have a certain voltage magnitude and angle, as well as in bus 2. So there must be an angle difference between the bus voltage at bus 1 and bus voltage at bus 2. So we will let our V2, the voltage at our bus 2, to be our reference at an angle of 0, and the power factor of the load is also assumed unity, or at power factor of 1.0. Then the current must be in phase with the voltage. So if we assume the power factor of the load here to be equal to unity, then this current that flows or that is supplied by the generator will be in phase with the voltage V2. So if our reference voltage is V2, then our I would be in phase, or it has a direction similar to V2. Now, a voltage drop occurs along the transmission line because of the current and the reactance of the line. This voltage drop is equal to I times XL and is 90 degrees with respect to the direction of I, because the angle of XL is 90 degrees. No? If we consider that ZL is equal to R plus GXL, now with R equal to 0 or being neglected, so our ZL is just equal to JXL. So J here will bear an angle of 90 degrees. So that's why our XL will have an angle of 90 degrees. Now to find B1, we add IXL to V2 as shown. So this is our reference phasor voltage V2, and then uh, we add the reactance drop along the line IXL 90 degrees with respect to the direction of the current. So it is this now IXL, and the hypotenuse of the two, adding V2 and IXL, will be our voltage at bus 1 or V1 with this angle delta. So V1 writing in phasor would be equal to V2 plus JXL. So from the diagram, we see that our IXL here would just be equal to the hypotenuse V1 times the angle, sine of the angle delta, so V1 sine delta. Or solving for I, this would be equal to V1 over XL sine delta. Now, however, the power drawn by the load is equal to V2 times I, that is our power, drawn by the load. And substituting the value of I, so we have V2 times the quantity V1 over XL times the sine of delta. So simplifying, we have P is equal to V1 times V2 in magnitude times over XL times sine of delta. Now we call this the coefficient of sine delta as the maximum value, because delta can take only value from -1 to 1, so maximum value of delta is 1. So when this is 1, so okay, the maximum value of our P would just be equal to V1 over V2 over XL. And we just call this as our P max. So our equation for power, therefore, would be equal to P max, okay, sine delta. So this is an equation, okay, relating the power generated by our generator and the rotor angle of our, okay, generator, which is, okay, the angle of the voltage at its terminal, okay, V1. Now, take note that the delta here is the voltage angle difference between the two bus, okay, voltages between V1 and V2. Now, since we choose V2 to be our reference, okay, phasor to have an angle of 0, so actually this delta here represents, okay, the rotor angle of the generator with respect to its terminal. Okay, so delta is not the impedance angle of the line connecting the two buses. Okay, so we have to take note that this delta here is not the impedance of the line between bus 1 and bus 2. Now, when the two buses have the same voltage angles, okay, the delta would be equal to 0 and there will be no power flow because, okay, P equal to sine delta. So if delta is equal to 0, sine 0 is equal to 0. So therefore, P is equal to 0. Now, the graph of the power angle equation, therefore, is shown here. So, drawing, okay, the vertical axis as our P and our horizontal axis as, okay, delta. And now we plot, okay, the equation P is equal to P max, okay, sine delta. So, the graph of this function is, okay, starting from 0, so it goes up like this, no? Which is half of the sine curve. Okay, now it does not continue to the negative side of or the second half cycle of the, okay, sine function because we do not have negative power. So it only stops at the at 180 degrees, which is this, okay, representing half of the, okay, sine wave. So we have here the maximum power that occurs at 90 degrees, now when, okay, delta is equal to 90 degrees. Then at other values of delta, okay, the value of P is less than the maximum. Now we will consider, okay, how to increase, okay, the power flow, okay, generated by our generator, okay, to supply the system. So number one is, okay, by increasing, okay, the voltage of the generator, okay, V1 up to its maximum allowable limit, assuming, okay, the load voltage V2 to remain, okay, constant. So previously we had a phasor diagram, okay, representing our bus voltage V2, which is chosen, okay, to be our reference, and then with unity power factor, we had, okay, the current flowing or drawn by the load equal to I1. So I1 has the same direction as our V2 because of the unity power factor. And then we add to V2, okay, the reactance drop along the line, which is I1XL. So the hypotenuse or the sum of the two is our hypotenuse, okay, V1. So representing, okay, the voltage at bus 1. Now, with this magnitude of V1, okay, we had, okay, this angle delta 1. So this delta 1 here makes possible, okay, the flow of power from bus 1 to bus 2. Okay, because this delta 1 here is the angle between, okay, the bus voltage at bus 2 and the bus voltage at V1. So we said that if there is no angle difference, okay, between the bus voltages at bus 1 and bus 2, then power cannot flow. So with the delta 1, okay, we had, okay, power being delivered by the generator. Now, since we want to increase the power generated by our generator, maintaining the voltage at bus 2 to not to be the same as before. So B1 can only increase, okay, the tip of B1, okay, can only move, okay, along this line, okay, with constant B2. Okay, so moving the tip of B1 to this new point where we call as, okay, the new hypotenuse as B1 prime. Okay, the system will draw, okay, another current, a different current, okay, from the previous one, which we call as I2. Now, it is necessary that the current has to increase, okay, because this reactance drop along the line, okay, need to increase from this value to this value. No? So, with the same XL, so it is necessary that the new current I2 should be greater than the previous current, okay, I1. So with this new value of reactance drop I2 XL, so we have this, okay, line. And so therefore adding B sub 2, okay, and this new reactance drop, okay, will give us the new voltage, no, to our bus 1 terminal. Okay, so we call this as B1 prime. Now, we also see that the, okay, angle of bus 1 also increased now from delta 1, okay, to delta 2, as shown here. So, increasing the voltage at bus 1, therefore, will necessitate, okay, the increase in current supply and also the increase in the okay, voltage sa terminal angle of our bus 1, which is actually the rotor angle of our generator. So, going back to our, okay, power angle curve, okay, with this equation P is equal to P max, okay, sine delta. Now, increasing the generator voltage, okay, to increase P also increases, okay, the generator rotor angle, okay, delta. Now, so since we are talking about, okay, the relationship of the power generated by the generator, okay, and the generator rotor angle, okay, delta, we see that following along this curve. Now, if we started at this point, say, let us say this is point 1, where we have the value of the rotor angle as delta 1 and the value of the power delivered by our generator as P1. So we have this. Now, to increase the value of P, now we want to increase the value of P. So, okay, P has to increase, no, from P1, okay, to a new value P2. So we draw a horizontal line, okay, from P2, okay, to intersect with this power angle curve, and then we drop, no, a vertical line to the horizontal axis. So this defines our new rotor angle, okay, delta 2. So increasing power, okay, of our generator necessitates, okay, the increase of the rotor angle from delta 1 to delta 2. Now, the second method of increasing, okay, the flow of power, okay, from our generator, okay, is by reducing the XL between the two buses, no, the reactance of the line. Now, one way to do this is by adding identical transmission line, okay, in parallel with the first. So, if we draw our network diagram, okay, we have our generator now. This time we have two lines, okay, going from bus 1 to, okay, to bus 2, and then now we have here the load. So when the reactance of the line is one line is XL, now the combination of the two, or the equivalent reactance of the two, would be just 1/2 of XL. So we have XL over 2. Now when XL is half, now the power also becomes twice now of the uh, first one. So meaning okay, our P max 2 will be 2 times, okay, P max 1. Okay, so this is it. Okay, when, of course, when our new XL is XL over 2, okay, so we have here XL over 2, so we have here, okay, 2 will go up here, and then therefore, this will just be equal to 2 times this one, which was our P max 1. Okay, when now we had only one line. So when we had two lines, okay, our uh, okay, power would be equal to 2 times this, no? V1 times B2 over XL times delta, because we have now two lines uh, between, okay, bus 1 and bus 2. So we see here that, okay, we have, okay, doubled, okay, the power that can be delivered by our generator, assuming that, okay, our generator has still enough capacity to deliver this, okay, much of power, no? The being twice the maximum power of, okay, the first. Now, this is the direct way of okay, decreasing, no, the total reactance of the line. Now, actually, if we do not need, okay, another line to be constructed, okay, what we can do to reduce XL is to increase, okay, the size of the conductor, because the inductance of the conductor is uh, equal to 2 times 10 to the minus 7 ln of DEQ over D sub S. So the D sub S is the self-geometric distance of the conductor. So making D sub is large, okay, means we have to increase the okay, diameter or radius of the conductor in order that its inductance would be, okay, reduced. Okay, so that is one way of reducing the inductance of the line, making use of larger, okay, conductors. Now, actually, in effect, when we have, okay, two similar lines being constructed, okay, to double the transmission of power, now actually we are in effect, okay, increasing the equivalent size, okay, of the two conductors. So combining the two conductors, we have now a larger conductor if it is to represent as one conductor. So in effect, we are reducing, okay, the value of XL. So that's, okay, the second method of increasing, okay, the flow of power, okay, from our generator. Now, the third way is by increasing, okay, the generator voltage angle delta. And how? Okay, to do this, okay, now by adjusting the setting of the generator governor to allow more steam, okay, for steam-driven generator, okay, to flow through the steam turbine, okay, we can increase, okay, also the power, okay, that can be delivered by our, okay, generator. So again, looking at the power delta curve, okay, when PM increases, okay, the voltage angle also increases. So as we have seen last time, that if we have this initial point, okay, so this is, okay, the original operating point where our turbine is delivering this mechanical power PM1. Okay, and our generator has this rotor angle, okay, of delta 1. Now, actually, when the generator is normally operating, our this PM1 would just be equal to our PE1. Okay. Now, when we want to increase, okay, the, okay, mechanical power, and that is also increasing the electrical power of our generator. Okay, by supplying more steam, no, to the steam turbine, so our mechanical power increases, okay, from PM1 to PM2. But this follows along this, okay, curve. Okay, so our electrical power also at the new point, okay, would be equal to our PM2, okay, and our generator has this rotor angle, okay, delta. So following, okay, this curve, we can, okay, increase, okay, steam supply to our steam turbine, and our generator will also generate, okay, more power, okay, by increasing its, okay, rotor angle now from the original, okay, operating point, okay, to a new operating point. And if we further increase the supply of power, okay, there is a possibility that this maximum power will be reached, no? So there is a corresponding mechanical power, which is also equal to our electrical power, okay, when the sine of the rotor angle is equal to 1, and that corresponds to a rotor angle of 90 degrees. Now, as more steam is fed to the turbine by the governor action, okay, the power produced may reach the maximum or Pmax when delta is 90 degrees as we have shown. Okay, then however, as more steam is fed to the turbine, okay, the voltage angle of bus 1 is already more than 90 degrees. So meaning we can still supply, okay, more steam to the turbine, and the rotor angle now increases beyond, okay, 90 degrees. So we see that from the sine curve, after 90 degrees, okay, the value, okay, of power, okay, becomes or is going down. So from the P delta curve, okay, we see that PM begins to decrease, no, as sine delta is now less than 1. So we have seen that for a given load, okay, we have two, okay, equilibrium points, no, along the power, okay, delta curve. So okay, this is our power angle curve given by this equation, P equal to P max, okay, sine delta. Now, okay, this is our power angle curve as we have seen. Okay, that for any condition, okay, of our turbine generator, okay, the power that can be delivered from the by the generator, okay, may vary, okay, along this, okay, curve. So, for example, for a given load, okay, the initial or the operating point of our generator is point A, where it corresponds to a mechanical power, okay, PM 1 or just a PM, and then at operating point A, we have a corresponding angle, okay, delta A. So this is our equilibrium point, no, meaning our generator will be operating, okay, normally at this point where our mechanical power is equal to our electrical power, and our generator has this rotor angle, okay, delta A. Now, however, if okay, we have to increase the supply of steam to our turbine, okay, the power delivered, okay, by our generator, okay, increases along this curve, no, and after reaching the maximum, okay, the mechanical, okay, power, okay, begins to decrease until it reaches this another point B, no, which levels to our initial point B along, okay, the curve. So this point B is what we call as the second equilibrium, okay, operating condition of our turbine, okay, generator. Okay, now our turbine generator can still operate, okay, normally at the point B. Now, however, if the rotor angle, okay, increases, okay, further beyond, okay, delta B, so meaning at this portion, okay, our generator is no longer stable. No, it is already unstable because at this point, okay, the mechanical power is less than, okay, the electrical power, and the our generator will absorb no power, okay, from the system instead of delivering power from the system. So our generator will be unstable here. Okay, whereas operating up to point B, okay, the our turbine generator can operate, you know, with a variation of the steam supply to our generator to be along, okay, this side. Okay, so as we let more steam, okay, to the turbine, the generator voltage delta, angle delta, merits, okay, delta B, no, the second equilibrium point where PM is equal to PE also. Now increasing delta B and delta B, okay, makes the system unstable because PE becomes greater than PM and the power flows back, okay, to the